Energy is conserved. You probably already know this from classical mechanics, for example, where you have kinetic energy, something that's moving, for example, a ball bouncing, and it goes up and it loses kinetic energy and it's converted to gravitational potential energy. And that gravitational kinetic energy comes back down and converts it back to kinetic energy. But the total energy, the sum of the two, as long as it's not losing energy due to heat or friction or something, it's going to remain constant. You probably don't know that that's exactly what the Schrodinger equation says. When you look at the form of the Schrodinger equation, you have E on one side representing energy. You also have on the other side something representing kinetic energy and something representing potential energy. And the Schrodinger equation says that if I measure a system, the energy is going to be the sum of potential and kinetic energy. The question is, why do we write it in such a confusing form? Why not write it like we do in classical mechanics? Well, if you write the Schrodinger equation in that specific form, it actually enforces something about quantum mechanics. That is that energy is quantized. You can only have certain energies. In classical mechanics, something can have 5.1 joules, it could have 5.11 joules, it could have 5.512 joules, all sorts of things. Quantum mechanics, there's only certain energies it can take. And so there's a question you could ask for a given system: what energies can that system take? And if you've taken undergraduate physics, you may have used this book here, a classic by Griffiths, to solve for the energies that specific systems can take. A system, of course, is represented by the potential it's in. So you've looked at things like the infinite square well, the finite square well, the quadratic harmonic potential, all these sorts of things. And analytically, you can only look at very specific systems. But I'm here to tell you on the computer how you can solve for the discrete energies of any quantum system. So here's a little blog post I wrote not so long ago about this subject. You'll see that I have the Schrodinger equation written up here. Kinetic potential is full energy, and then our boundary conditions. Our particle is confined between psi is 0 and psi equals L. And there might be stuff going on in the middle, but we know it has to be bounded between those 2 points. This would be like a bounded Schrodinger equation. This is what's known as a regular Sturm-Liouville problem. It's a mathematical problem. This is the beauty of writing energy conservation in this way, because it enforces that there are discrete energies. There's infinitely many of them, but they're discrete apart. So by writing the equation in this way, you say, okay, there's only certain quantized energies that the statement can take. And there's a few statements about the eigenfunctions. But I would say for the point of this video, I'm really focused on the energies of a quantum system. And of course, the infinite square well is the case where V is equal to 0. So it's bounded, but there's no potential in the middle. And then you know what your energies are, of course. So we need to massage this equation a little bit before we put it into Python. And so I'm going to sort of go through these steps. Firstly, we choose h bar is equal to 1. This is common in physics all the time, and it sets our units. The other thing I do here is I multiply by m, so the equation looks like this. But we have that quantity x, right? And x has units of position. And I don't like that when I'm on a computer. I want to make everything dimensionless. So I'm going to make the substitution y equals x over L. Remember, L is the length that we said that the particle is bounded in. So I make the substitution y equals x over L. And I plug this into our equation, and we now get this equation here. So here's our new equation once we substitute in y equals x over L. You'll see it's written like this. The boundary conditions are expressed like this. So now we're between 0 and 1 instead of x is 0 and L, 0 and 1. It's very tidy mathematically. And then we also have our equation that looks like this. And everything's written in terms of ml squared v and ml squared e. And you could think of those as like being their own things. Instead of thinking about what is v, or what is the potential for the system, think more about what is ml squared times v. And that will help when solving this numerical problem. When you think about things as like everything comes packaged together. And when we define our potential, we'll define ml squared times v. So now we need to massage this equation to be in discrete form. And as always, I have my lovely program Paint here to help us think about this. So here's some function, right? And suppose we have a function f of x that looks like this. And this is continuous. But we can split it up into a bunch of discrete points. Right? And maybe here as well. And I might call this f, the first point f underscore 0, the second point f underscore 1, f underscore 2, f underscore 3, all the way up to maybe the last point here is f underscore n. So I have a grid now of f0 to fn of many discrete points. And I can write a differential equation in terms of these points. And it turns out that if you want to find the second derivative at a point and you know what the f's are, you can. And the formula is given by this here. The second derivative is equal to this. And delta x is just the spacing between these points here. So there's your delta x. And now we can write second derivatives in terms of these grid of points. So we're going to solve the Schrodinger equation over a grid of points. And we write our second derivative like this, and we plug it back into our Schrodinger equation, and we now get this. And it might not seem like a lot to you, but there's a real beauty in this equation here. We can manipulate it to look like this. We have a factor times psi j plus 1, plus a factor times psi j, plus a factor times psi j minus 1 is equal to a factor times psi j. It might not look special to you now, but what this is it's many systems of equations. And if I bring up Paint here, it's like saying there's something that occurs in this interval here. There's something that occurs for these 3 points here. There's something that occurs for these 3 points here. And you'll see that how I write that down here. We can plug in any value of j we want, and we get an equation, right? For those particular values of j. I can plug in j is equal to 1. And then I get psi 2, j1, psi 0 is equal to e times psi 1. What that is an equation that tells us about this first blue gap here. It just tells us something about these 3 points. Then there's another equation that tells us about these 3 points. And there's another equation that tells us about these 3 points, all the way up to an equation that tells us about these 3 points. And they're all kind of overlapping here. Now, I can write this as a matrix equation, like this. And you'll see that now I have a matrix. So I have a bunch of things times a vector is equal to a number times a vector. This is an eigenvalue equation for a matrix. A few things to note. The vector only goes from psi 1 to psi n minus 1, but I also have psi 0 and psi n as my initial and final points. But that's where the boundary conditions come in. They tell us that those are equal to 0, so I don't need to consider them, right? Otherwise, I'd have another row here, but it's equal to 0 anyways. So I just need to find for psi 1 to psi n minus 1. And then the zeros automatically come packaged with the solution. And then we just plot the other points in the middle. Now, this equation essentially completes our journey here like this. We define our potential, V. And we get also our, if I bring this up, you could also think of if this is our potential. Instead of F, this would be V0, V1, V2, V3. It's defined over that grid. And then we can plug in those values in this matrix. There's going to be 3 diagonals on this matrix. It's a tri-diagonal matrix. So it's not full. It's going to be a big matrix, but it's only going to be entries on the 3 columns. And as you'll see when I cut to Python shortly, that there's very simple ways of solving this problem. So we need to find what values of ml squared e are allowed for this. And depending on v, it's going to be different. So in other words, depending on our potential, we can plug in any potential we want here. We'll have different values of e. And this is solving the Schrodinger equation for any potential. All right, guys, so here I am in Python. I've copied the equation that we derived on the blog. This is an eigenvalue equation. It says you take a matrix, you multiply it by a vector is equal to a constant times a vector. there's only certain constants that works for, and as such, there's only certain energies that we're allowed to have in our quantum state. And we have our boundary condition as well. This is also the Schrodinger equation, written in terms of finite dimension, right? N. The true Schrodinger equation is as n goes to infinity, and we have those infinite dimensional vector spaces you've probably heard about. But here, we're using a finite approximation to get a good estimate of the energies that we have. And if n is large enough, it will be a really, really good estimate of the energies. So let's define a good estimate value for n. I say let's take n is equal to 2000. And we also need to be careful about defining delta y here. Delta y, right, if I bring up this here, suppose I have psi 0 up to psi n. Here's psi n. Here's psi 0. Then I know that if there's n points here, that n times dy is equal to 1, because dy is just a little interval like this. So I say n times dy is equal to 1. I'll let you think about that a little bit. And so dy is equal to 1 over n. We also need to get v1 to vn as well. And so we need an array of y. So y is equal to np dot array. We'll do lin space. We'll go from 0 to 1. And we need n plus 1 points. That's because we also have psi naught. We have psi 1 to psi n, and we also have psi naught that we need to include. And so we can use this y to get v1, v2, v3, all the way to vn minus 1. You can also think about these points as being v1, v2, v3. And if we get our arrays of y's, then we can also get our v's as well. So let's define our potential. Remember, we have to define ml squared times v. So I'll write it like this. It's a function of y. And we'll return, I'm going to say, a quadratic potential that's centered in the middle of 0 to 1. So I have to multiply it by x minus 1/2 squared. You might be confused about this factor of 1000. That's essentially saying, right, because notice we're defining ml squared v. This 1000 could be thought of making L really, really big. And if L is much bigger than the geometry of the problem, it's as if we were solving for a particle that was unbounded. So even though we have a bounded equation, if we consider L big enough, it's as if it's another approximation that we're approximately in a unbounded system. So again, we need to do this numerically, but something you wouldn't do necessarily not numerically. And so we can we can plot this as well. Of course, I put x and not y here, and I can plot these. And so we just have a nice quadratic potential here between 0 and 1. So now we basically have everything we need. We need to find the eigenvalues of this matrix. And you'll note that all the information in this matrix is contained in the main diagonal and the two off diagonals because it's tri-diagonal. So everything is contained in this. So we'll just define those two things here. You'll note that we're missing psi 0 and psi n, right? So in total there's n plus 1 points, but we don't have 0 and we don't have n, so we subtract 2, which means this matrix is n minus 1 by n minus 1. In other words, we don't take v0 and we don't take vn. So I'll say the main diagonal, which I'll call d, we have this 1 over dy squared. And then we add v m l squared v of y, but we don't take the first point and we don't take the last point. And our off column, e, is just this repeated over and over, and this off column is of length 1 less than the main diagonal. So I'll call this e, and it's just equal to 1 over 2 times dy squared. And it's just repeated over and over, so I'm going to multiply that by an array of MP1s, and it's going to be one less than the length of d. So now I have my main diagonal and my off diagonal. And using this, we can plug this straight into the SciPy tridiagonal method, and this will give us our eigenvalues eigenvalues, or our eigenenergies, and our eigenfunctions, V, eigenvectors. And we basically just need to give it D and E, and it's very simple. And we have our eigenenergies and eigenfunctions. We can plot our eigenfunctions. Because of the way it returns V, we need to transpose V, because our eigenfunctions are actually this, then this is our first eigenfunction. So it's a little bit confusing. It's across columns. So we transpose it, and then this becomes our first eigenfunction. So we can plot these eigenfunctions. Let's plot the first 4. And these look very similar to the eigenfunctions you're probably used to, and for the quadratic harmonic potential. And of course, the probability is proportional to the square of them. So I can also square them, and you'll see that they look symmetric. This is like related to the probability density of finding the particle. We can also plot the energies. Let's make a bar plot of this, and we'll plot the first 10 energies. So this is just for the bar plot, and then we'll go W 0 to 10. And you see that we have our energies here. These are the eigenvalues. Remember that the eigenvalues are equal to ml squared times E. So the real y label would be plot.y label ml squared times E. And you'll notice that technically this should be an integer. It's not. The dimension, this is not a dimensionless quantity, although it should be. That's because we set h bar equal to 1. And at the end of the problem, we need to make our dimensions work. In order to do this, we have to divide by h bar squared. This is a trick that you use in later physics. You solve your problem assuming h bar is equal to 1, and then you put it back in at the end to make all the dimensions work. And so this is what our y label is. So if we want to get our first, say our second energy, which is approximately equal to 100, we would say ml squared E over h bar squared equals 100. That means that E is equal to 100 times h bar squared divided by ml squared. That's how you extract your energies. Now, this was a simple problem. This was the harmonic potential, and you've probably already solved this analytically in a physics course you've taken. Let's do something a little bit more fun. So what I'm going to do is, instead of making a harmonic potential, I'm going to put a little Gaussian spike somewhere in that well. So a Gaussian spike, I'll leave this 1,000 here. And Gaussian is of the following form: x minus 0.7. That's where it's centered. It's centered at 0.7, between 0 and 1. And divided by 2 sigma squared. And I'm going to make sigma 0.05. And this should be squared as well. So here's our new potential. Let's look at the eigenfunctions and eigenenergies as well and see what happens. Once again, I accidentally used x instead of y. Now, this is going to be interesting. Look at this. The first energy eigenfunction is to the left of the bump. I should probably plot the bump as well. So here's our little bump in potential located right here in the well. So we're bounded in this well, and there's this bump of potential. The first eigenvalue squishes in here to the left of the bump. Then the second one, which is the orange, also squishes in here. The third, which is the green, shoves its way in here, which is mysterious, and it's very interesting, right? And then the next highest one is the red, and it once again goes to the left of the well. This is something that you probably wouldn't know if you were to try to solve this analytically. It would be very tough to get this result, that you have 1, 2, and then third goes to the right. And our energies, you know, it's another interesting thing as well. They're not, you know, straight up. They're kind of more jagged as you go up. Anyways, I encourage you to try this with as many potentials as you want. Get some interesting results. I hope you enjoyed this video. If you like this content, please like and subscribe. Thanks, guys.